Good and everyone, it's a good morning. And today we are going to explore a topic that is rapidly moving from the realm of science friction into uh, everyday's reality, drone delivery. As you have seen from the images in the slide, the idea of an autonomous aerial vehicle carrying a package over a bustling city is no longer just a futuristic concept. It represents a fundamental shift in logistics and a newfound regard uh, for how we move goods. Here, um, we are going to talk about the functionality behind these services to peek under the hood and understand what makes these amazing machines tick. At its core, the concept is straightforward. We are using unmanned aerial vehicle or UAV specifically designed and equipped for purposes of transporting goods and packages from one point to another. But the simplicity of the idea believes that incredibly sophisticated technology required to make it work safely and efficiently. The real magic lies in how these drones navigate, communicate, and make decisions on their own. The foundation of their operation relies on the suite of communication and navigation technology that most of us use every day. Primarily, these drones depend on Global Positioning System or GPS for navigation. Just like mapping application on phone, GPS allows the drone to pinpoint its exact location in real time and allow a meticulously planned route to its destination. This ensures unparalleled accuracy, whether it is flying over a sprawling suburbs or navigating through a dense urban environment like the one in the picture. But GPS is just one piece of the puzzle. For short range communication and data transfer, these uh, UAVs also rely on technologies like Wi-Fi and Bluetooth. Wi-Fi is crucial for receiving uh, complex flight path, sending back live feeds for monitoring, and communicating with central command center. You can imagine a drone connected to local Wi-Fi network at a distribution center to get its instruction for the next delivery. Bluetooth, on the other hand, can be used for very last step of the journey, that final handshake at the drop-off point. It could allow the drone to securely communicate with smart delivery boxes or even the customer's smartphone to, to confirm the successful and secure handshake of the package. This brings us to what truly makes these cargo drones autonomous. The integration of artificial intelligence and Internet of Things, often refers to as IoT. AI is the brain of the operation. It is what allows the drone to do more than just following a line of map. AI-powered systems are responsible for real-time obstacle avoidance, enabling the drone to detect and navigate around building, tree, power lines, and even other flying objects. This also manages dynamic routing planning. If weather condition changes unexpectedly, or if a new restricted flight zone appears, the AI can recalculate the fastest, safest, and the most efficient path in an instant. Internet of Things or the IoT is what connects the drone to the wider logistic network. Each drone is essentially a smart connected device. It constantly transmits data about its location, battery life, cargo status, and surrounding environment. This stream of information provides complete transparency for both the logistic company and the end of consumer, allowing everyone to track the package journey in real time. It's seamlessly fused of advanced hardware, precision navigation, and intelligent autonomous software that defines the functionality of modern delivery drones. So we have seen the sophisticated technology that makes drone delivery possible. But the crucial question here is, what does this technology actually do for us? Why invest in developing or deploying these systems? This slide outlines the core advantage, which together paints a compelling picture of the future where logistics are faster, smarter, and more efficient. Let's break this down into these benefits. First and foremost, drone delivers delivery offers significant advantage in the terms of efficiency, both in labor and in navigating our increased crowded advanced landscape. The point about reducing manpower is the key. The traditional delivery system requires one driver for each vehicle on the road, which a drone delivery system, a single highly skilled operator can potentially monitor and manage an entire fleet of autonomous drones from a single command center. This dramatically changes the economy of last mile delivery. It's not about replacing jobs, but rather evolving them towards more technical role focused on the fleet management, logistic, and drone maintenance. Coupled with this is the ability to completely avoid road traffic congestion. Every major city in the world struggles with gridlock, which leads to unpredictable delivery time, wasted fuel, and increased pollution. Drone simply rises above it all, but operating in a low altitude airspace, they bypass traffic jams, accident, and rush hour delay, entirely offering a level of predictability and reliability that ground-based vehicle simply cannot match it. This also has the secondary benefit of reducing the number of delivery vans on our street, which can help the congestion of everyone. The second major advantage is the incredible speed and the precision that drone brings to the table. As the slide notes, this is achieved through automated software that enables accurate location identification because drones aren't bounded by road. They can travel in any straight line from the dispatch center to the delivery address. There are no stop signs, no red signals, and no winding street to navigate. A delivery that might take 30 minutes to an hour by car could potentially be completed in 10 to 15 minutes by a drone. This is a game changer for time sensitive deliveries like hot food or urgent medication. This speed is complemented by precision. By using advanced GPS and sensor technology, a drone can be programmed to land in very specific, very predetermined spot, vacuum, a designated landing pad on the balcony, or a secure drop box with accuracy within few centimeters. This level of precision drastically reduces the risk of package being lost, stolen, or delivered to a wrong address, enhancing both security and customer satisfaction. Finally, let's consider the immense route flexibility and reduced reliance on traditional road infrastructure. A delivery truck path is dedicated entirely by the available network of road. The drone's path, however, is more dynamic. Its route can be optimized in three dimensions, allowing for nearly infinite path variation to ensure quickest and safest journey. This flexibility also makes it possible to serve locations that are difficult or impossible to reach by car. Think of remote communication separately by river with no bridge or homes located in an area with poor or non-existing road access. For drone, these geographical barriers are irrelevant. This fundamentally changes our relationship with infrastructure. While drones do require their own support system, like charging hub and air traffic control, they lessen the wear and tear on our expensive and road network, carbon intensified road network. By creating a new layer of logistic in air, we can build a more resilient and accessible delivery system that isn't solely dependent on the limitation of road. These advantages are transforming logistics, and as we see, the next we are having a profound impact in the true in the some truly critical areas.
Our last discussion concluded with the introduction of dynamic observer theory, a powerful method for estimation that uses a model of system physics. Today, we'll focus on the most widely used implementation of that theory in robotics and aerospace, the extended Kalman filter. The extended Kalman filter is an extension of Kalman filter for nonlinear system. The original Kalman filter is a landmark achievement in estimation theory, but it has one major limitation. It only works for systems whose dynamics and measurement are described by linear equation. Unfortunately, the physics governing aircraft flight are highly nonlinear. The EKF is an indigenous adaptation that allows us to apply the power of Kalman filter to these real-world nonlinear problems. At its core, the EKF's purpose is to estimate the state of dynamic system from a series of noisy measurements. This is precisely the problem we need to solve for our MAVs. We have a dynamic system, the drone, and a series of noisy measurements from its sensor. And we need to produce the best possible estimate of its true state, such as its altitude, velocity, and position. The key innovation of the EKF is how it handles the nonlinearity. Instead of solving the nonlinear problem directly, it cleverly sidesteps it. The EKF uses linearization around the current estimate to apply the standard Kalman filter. The diagram on the slide provides a great illustration of this process, which it is called as passing Gaussian through linearized approximation. Imagine the system has a belief about this current state, represented by the bell curve on the left. To predict the next state, this belief must be passed through a nonlinear function. The EKF approximates these curves with a straight line, a tangent, at the point of the current uh, best estimate. It uses this simplified linear model to project belief forward, resulting in new adapted belief about the state. Mathematically, the EKF handles nonlinear state transition and observation model through Taylor series expansion and Jacobian's matrix. The first order Taylor series is the tool used to create the linear approximation, and the Jacobian's matrix is the result of this process. This technique is not just an academic exercise, it is absolutely critical for the navigation, tracking, and control system. In fact, the EKF is widely used in MAVs, micro air vehicle, for state estimation. It is the workhorse algorithm that runs at the heart of the most modern autopilots, fusing the data from IMUs, GPS, and other sensors to provide a single, robust estimate of the drone complex state. Now that we have the highest level understanding of what the extended Kalman filter is, let's look more closer at how it operates. The EKF is specifically designed for addressing nonlinearity in system propagation and measurement model. This means it can handle both the complex physics of the drone motion and the nonlinear way in which its sensor relates to its state. The EKF accomplishes this through a step-by-step process: prediction and updation. The first phase is the prediction step. In this step, the filters use its internal model of MAV's dynamics to project the current state forward in time. It propagates the state estimate and error convergence using non-linear model and its Jacobian matrix, especially based on the last known state and the command sent to the motor. It makes an educated guess about where the drone is now and how it is oriented. Crucially, it also predicts it is now uncertain, known as the error convergence. It also it is also predict that it is perfect and uncertain will grow over time without new information. The second phase is the measurement update. This occurs when the new piece of the data arrives from the sensor, like GPS or an accelerometer. The filter then corrects the state estimate and, and a covariance based on the sensor measurement and the Jacobian of the measured model. It compare its prediction from the last step with the accurate measurement. If the measurement is close to the prediction, the filter becomes more confident in its estimate and reduce its uncertainty. If the measurement is significantly different, the filter adjusts its estimate, weighting the new measurement against its predicted based on how noise it is believed the sensor to be. This constant cycle of prediction and correction is what allows the EKF to track the true state of the system over time. Both of these systems are made possible through the process of linearization. The EKF uses first order Taylor series approximation around the current estimate to create a linear version of nonlinear model. This allows the powerful mathematics of the original Kalman filter to be applied. The filter is that provides a balance between computational efficiency and accuracy for moderately nonlinear system. It may not be as precise as more advanced filter, but it is a highly efficient, making it perfect for the embedded processor on MAVs. The AHRS evolution diagram on the slide shows this practically. Early autopilot firmware like Copter 3.21 uses simple methods like TCM and inertia NAV. However, later version processed to use EKF1, EKF2, and now we are currently at EKF3, demonstrating the industry's wide adaptation and continuous improvement of EKF as the standard of MAV state estimation. Now that we have established the theory behind EKF, let's look at this first and the most critical application in the MAVs, altitude estimation. This is the process of figuring out the drone's orientation in space, which is fundamentally to all aspects of its flight. The primary application of this specific EKF is that it estimates the roll and pitch angle of the MAV. While some observers also estimate, yeah, the core task of stability is getting a fast and accurate reading of the roll and pitch angle. The variables that the filter is actively trying to figure out are controlled in what we call it as the state vector. For this task, the state vector typically includes roll, pitch, and their rate, which can be mathematically written as x equal to chi theta p and q multiplied by t. This means the filter is simultaneously producing an estimate for four values: current roll angle, current pitch angle, current roll rate, and current pitch rate. To produce these estimates, the filter intelligently combines the data from two different states. The model integration shows how it works. The EKF uses the angular rate measurement for state propagation. This means it takes the high-speed data from the onboard gyroscope, the P and Q rates, and uses them in predicting step to project the altitude forward in time. However, because gyros drift, this prediction alone won't quickly become uh, won't quickly become accurate. Therefore, the filter also uses accelerometer measurement as output equation. The accelerometer provides a stable, long-term reference to the direction of gravity. In the update step, the filter compass into gyro-based prediction to the gravity vector measured by the accelerometer and uses the difference to correct from any accumulated drift. The result of the sensor is sensor fusion is majorly improving the accuracy over simpler technique. The EKF provide significant better estimate during accelerated flight compared to simple method. The simpler method that rely heavily on accelerometer can easily confuse during turn or fast forward flight because the force from acceleration combined with the force of gravity makes it difficult to know which way it is truly down. Because the EKF has a dynamic model, it can anticipate and account for this acceleration, maintaining a much more reliable altitude estimate even in aggressive maneuvers. Yes, ultimately, this robust and accurate estimation is essential for stable flight control and navigation system in MAVs. Without a trustworthy sense of this own altitude, a MAV cannot simply fly stable or navigate efficiently. Having seen how the extended Kalman filter is applied to the altitude estimate, we can now expand its scope to the even more comprehensive task of full MAV's navigation. This involves not just knowing how the drone is oriented, but also where it is going, and what environmental forces are acting upon it. The application of navigating EKF is to estimate a much larger set of variables. It estimates position, PN and PE, ground speed, which is VG, course, which is mentioned by X, wind, which is mentioned by WN and WE, and heading, which is mentioned by the letter chi. This state vector is incredibly rich. It includes MAV's position in north and east coordinates, its speed and direction of travel to the ground, the north and the east component of west vector, and its yaw angle or heading. By estimating all these states simultaneously, the filter can build a complete picture of MAV's situation. This comprehensive estimate is achieved through a process that can be thought as an advanced GPS smoothing. The filter integrates GPS position, ground speed, and control measurement like with a nonlinear propagation model. In this updated step, in this updated step, the EKF uses the measurement from the GPS receiver. However, in between these relative slow GPS updates, the filter uses its internal physics model driven by high frequency data from inertial sensor to propagate the state estimate forward in time. This process fills in the gap between the GPS reader and filters out the noise, resulting in smooth, high rate navigation solution. The enhanced performance of this approach is significant. The EKF produces much better navigation estimate than the simple low pass filter, especially in the dynamic missions. A simple filter on the GPS would be sluggish and lag behind the drone's actual movement, where the EKF's prediction model allows it to generate a much more responsive and accurate estimate during maneuvers. One of the most powerful features of this type of filter is its wind estimation capacities. By comparing the MAV's velocity through the air with this velocity over ground, EKF solved for the wind vector. This is a crucial capacity for path planning and energy efficient flight in outbound. Knowing the wind allows the drone to fly more precise path and conserve energy. Ultimately, this sophisticated estimation enables robust autonomous navigation even in a challenging weather condition.